No problem. OIST and Nic Shannon group and Pranay in particular and Shino madam in particular, because they really helped me to set up this visit. And I'm really enjoying my stay here, as how can you not as a visitor, I suppose. So today, I would talk to you about sort of a class of models, and models are generally interesting to us. So maybe I won't try to, I mean, Z2 quantum spin liquids, everyone must know what that roughly means. This one is unfamiliar probably. So the goal is to convince to you that something unfamiliar might perhaps be interesting to all of us. So this work is done in collaboration. Part of it is done in collaboration with Harsh Nigam from ICTS Bangalore. And for the people, I mean, there's going to be a generalized symmetries conference even at ICTS in the beginning of next year. So someone who is interested in visiting India might be interested in checking it out. I come from IIT Bombay in Mumbai, and I'm very thankful again to Japan for welcoming me. Okay, so I wanted to start on a slightly lighter note because of this funny name, I suppose. Is there was in the conference, there was a public talk by Zhu Ji Luo, and she made a nice little slide about, you know, when do you know you have sort of gone too much. She showed some examples of when we can recognize what is art and when something is kind of absurd in some sense. And whenever you have a new name in front of you, you are valid to wonder whether it's just forced upon without any good reason. And so I found it interesting that Marvin Key asked a question at the end, how do you know which is which? And especially, she didn't quite answer it. And she said, when you have some funny names given on a structure, and I'm thinking to myself, I'm presenting a poster on this funny name business. Am I doing something wrong? So how to motivate something that is, I'm giving it a new name. So you can always start by consider the model and then try to convince. But I've spent enough time with these models that I have some hindsight motivation to why you might find them interesting. So one way you can motivate it is you take the 1D Kitaev chain. So on a chain, you have alternating bonds have Ising couplings along x direction and Ising couplings along z direction. And just by using Kitaev representation, this simply reduces to a system of hopping Majoranas. And you can ask, how do you generalize this system of one-dimensional hopping Majorana system to higher dimension? And one of the answers that we are very comfortable with now is the Kitaev honeycomb model in 2+1 dimensions. And if you want solvability, this is quite a rigid, you can't do much different, non-trivially different than the Kitaev honeycomb model in 2+1 dimensions. However, you can sort of take it in a slightly different way. So when you go into the Kitaev representation, actually the Z2 gauge fluxes of, or the gauge fields of the Kitaev spin liquid actually become, all the gauge sectors become exactly degenerate in the one-dimensional system. And this is particular to one dimensions, that gauge fields cannot matter in one dimensions. And in 2+1 dimensions, we are familiar that the honeycomb model, the gauge fields give rise to gauge invariant fluxes, and those fluxes matter, i.e. they control the energetics of the problem. So from that sort of point of view, can you ask if this funny one-dimensional pure gauge effect or artifact, can it be in some sense sensibly generalized to higher dimensions? Okay, so at some level, the models that I'll talk about is doing this kind of generalization of the one-dimensional Kitaev chain. Another sort of, this is not as good a motivation, I suppose, but what if I take Kitaev toric code? And in the Kitaev toric code, I have the star terms and the plaquette terms, and they share two spins if they're nearby. What if I force them to have one spin sharing or a corner sharing geometry? What is the result? Sort of another. This is more of a, toying around kind of motivation. I, of course, didn't arrive at this anti-commuting business through this. So I'll try to tell you how I arrived at it. And so there was a previous work where I came up with a set of models, which you can think of as how to embed one-dimensional Jordan-Wigner spin-ons in higher dimensions. Okay. And so I was motivated by solvability. So the trick or the construction was you have these stack of one-dimensional system of Jordan-Wigner fermions. Okay, say let's say spin half XY chain and so on, and you couple them, but you couple them through some spins in between. So these extra sites are some extra spins in between, and the coupling you set up such that the coupling is orthogonal in spin space. So say this is spin half XY chain, then these orange couplings are in the Z direction, sigma Z, Ising in Z direction. So if you do this kind of orthogonal spin business, very reminiscent of the bond-dependent couplings in the Kitaev honeycomb model, you can use Jordan-Wigner transformation to even solve these high dimensional. And there's a good deal of flexibility in doing this construction. But this particular construction is what led me to the anti-commuting algebra. So what this is, basically, you can think of it as these stacks, these black lines, are a system which have on-chain Ising systems, so just standard Ising chain. And this spins in between the chains are like a classical spin liquid. They are, so I've indicated by, the spin doesn't really know which direction to point at. So it can, it can point in any directions. All of them are equidegenerate. And so you can think of them as some massively degenerate manifold, and it's like a liquid-like behavior. So one simple consequence of this is actually you will get a two-step entropy release in the spirit of the Kitaev spin liquid. So the entropy of these sort of liquid-like or paramagnetic spins will be released first as you heat it up. And then you will later on release the entropy in this Ising chains if it is gapped. Yeah.
So just to check so there's actually the orange connection isn't just an interaction, that's actually decorated with the spin.
Right, indeed. There are extra sites in between the chains. Yeah, okay. Indeed. So Kagome is where it naturally happens. And here we have put an extra decoration on the square geometry. Yeah. Any other questions? So this particular construction was actually realized by Nusinov and Ortiz really long time ago. And they were motivated by some orbital compass physics, but we can skip that. So some details. So as I said, it's a stack of Ising chains, and they're coupled by some intervening off-chain spins, which are in the orthogonal. The coupling is in the orthogonal spin space. And from the point of view of algebra that we so like, these extra spins, these off-chain spins, because it's just an Ising coupling along Z direction, the sigma Z is conserved. Just like in classical Ising model, all the sigma Zs are conserved. Similarly, these sigma Zs are conserved. It turns out for this particular construction, and none of the previous other constructions in that work, but we focus on this, there are additional conserved quantities on these orange bonds. So on these orange bonds, and you can think of them as just the standard Z2 Ising parity of Ising chain. So on this orange bond, there are three sites, this one, and this one. So the sigma x product on that is also conserved under the Hamiltonian, okay? But you can also see that these two Z2 conserved quantities actually do not commute, okay, when they share a site, okay? When they are nearby in some sense, they do not commute. And so this is an instance of an anti-commuting algebra. You have some conserved quantities which commute when they are far away, but if they happen to share a site, odd number of sites, let's say in this construction a single site, they anti-commute. So this algebra of local charges or local conserved quantities, I have given this a name, anti-commuting. And it's because of this algebra you are forced this spin liquidity on these, classical spin liquidity on these intervening spins, actually. So this was worked out in that previous work. So you can, but one might say from a model construction point of view, there's somewhat unsatisfactory point of view on this, which is because the sigma Z on these in between sites are conserved, Therefore, they are effectively classical degrees of freedom. And thereby, you might ask, is there a way of realizing this kind of an algebra in a fully quantum mechanical setting? Okay, so that's one way of, that's how I arrived at it. So this.
What do you mean by orange with IPL?
This one. So I take an orange segment and I take the product of sigma x on the 3 sides on that orange segment.
Every 3 sides.
3 sides, yeah.
You have Z interactions on the orange,
Right.
X interactions on the green.
Right. X, yes, on the green. Yeah, indeed. So very much like Kitaev honeycomb model, but with some extra bells and whistles.
So it wouldn't be a Kitaev honeycomb model topological decorate.
Yes, yeah. Yes. So if we forget about this decoration, then we actually would put the Kitaev chain. So x, z, z, x, x, y, y, x, x, y, y, then it would be Kitaev honeycomb. Slightly different. Yeah.
Okay, so
Yeah.
the spin chain.
Right. So the question is, how do you make this fully quantum mechanical? And this brings us to the first case. Of course, you motivated by considering a model, but there's a general structure. This spin liquidity is actually somewhat general. So before I state show the model, I would like to sort of make the statement, the general statement. So of course, we don't need for this audience the value of exact statements, but they're helpful, especially when there is no exact solvability. And the class of models that I'm going to talk about, as far as I know, I don't know how to exactly solve them. But one example of such statements is the Elidzo's theorem for Z2 or lattice gauge theories. And actually that concept has a lot of resonance with the structure in these models. So here's the statement. So if we have such local conserved quantities, Z2 local conserved quantities, which are anticommuting in the sense we saw, the orange product of 3 sigma x's and a sigma z, and there are extensively many of them, which was indeed the case in the previous model. And this is fairly natural with bond-dependent couplings. Then we are guaranteed that each, there's an extensive residual entropy in the ground state. There's an extensively degenerate manifold of ground states. Okay, and familiar examples would be classical spin ICs, and even to a certain extent the SYK type models. In these models, it turns out there is this degeneracy, but the counting is fairly simple, as we'll see. Yet it is non-trivial in my opinion. And this degeneracy is true for the entire spectrum. It is spectrum-wide true. And the second consequence, which is interesting to me, is any 2-point spin correlations actually have cancellations and they become 0. So there cannot be any magnetic ordering. So very much analogous to classical spin ICs, where you have so much, there's a whole degenerate manifold and therefore you cannot have ordering. In that very same sense, there are cancellations in this degenerate manifold. And in my work, I have shown that even the higher point correlations are somewhat featureless. And there's, at least my intuition tells me that you don't expect any symmetry breaking on them. So this is the statement. And now we'll consider the model. Okay. So this is, if you wish, a prototypical model. You take the square lattice, you decorate it, in this fashion. You color some of the plaquettes with this orange color and some with green. And on the orange plaquettes, you can have various kinds of couplings. So this shows, let's say a small Ising, 2-spin Ising couplings in one direction in spin space, sigma x, let's say. And on the green one, you have sigma z, Ising plaquette. So they are orthogonal in spin space. And so this, if you take this model, you will actually have arranged for the anticommuting algebra. And this works as follows. On, let's say, if these are the x plaquettes, so the couplings are in the x direction, sigma x. This quantity is conserved on that plaquette, product of sigma z's on those plaquettes. So that's the Z2 Ising parity on that plaquette, on a local Z2 Ising parity. And that's very by a very similar token on the other set of plaquettes, the other product of sigma x's is conserved. And now you can immediately see that whenever these two plaquettes are sharing a site, these two quantities are not going to commute, but rather they are going to anti-commute, right? So this is another, but of course, when they are far away, so this plaquette and this plaquette, they do commute. So this is another instance of an anti-commuting algebraic structure. And because of the construction of the model, there are no local site, local conserved quantities. So it's a fully quantum mechanical system from that point of view.
Sorry, can I just clarify?
Please.
So here in this picture, what anti-commute is for?
So this local Z2 parity on this plaquette, and this local Z2 parity conserved.
So they only meet at that one point.
Right.
Right.
The spins are on the vertices of the lattice. Indeed. So they anti-commute. Otherwise, everything, all other pairings commute. Yeah. So you can, So you can see there's some analogies to standard spin half degrees of freedom. Spin half degrees of freedom also follow Pauli algebra. On site they anti-commute. Off site they commute. Here also there is that sense that when they're nearby they anti-commute. Otherwise they commute. However, it's a sort of more intricate interconnect. Yes, please. Okay, but it has an interconnected structure. So if you have a collection of local spin halves, they are just distinct local algebras. But because of this interconnection business, this is one single anti-commuting, many body anti-commuting infinite algebra. No.
So what you've got, if I'm understanding
Right.
You have something like using gauge degree of freedom on one side of plaquettes,
Right.
using gauge
Right.
associated with the other axis.
Indeed. And they don't commute. Yes, and they don't commute. Yes. Yeah, that is the mathematical fact. Indeed. It's just trying to draw some analogies to something that we might be familiar with. So you have these. So yeah, indeed. So spin variables generally refer to degrees of freedom, but this structure is in the structure of the local conserved charges. So that difference is there. But if those gauge charges had some dynamics, then you can think of them some as degrees of freedom. But the algebra is system-wide, so to speak. And so for this model, you can do the degeneracy counting. I won't get into it. It's in the paper. It implies a residual entropy of k log 2 per unit cell and not per spin. So this is non-trivial. And the unit cell has the bigger, it's not, it has 4 sites in the construction. And furthermore, as I said, once you have this local anti-commuting structure, any 2 spin correlators of this form, sigma x, sigma z, whatever, in this degenerate manifold, they cancel and they become 0. And in fact, even dynamically, that is true. This is, even that, yeah.
So this is where you want to invoke Elitz's theorem.
In a sense, yes. That cancellation is a form of Elitz's theorem. Indeed. So one way of sort of hand-wavingly saying it is that the Elitz's theorem you throw out, you have these redundant copies and you don't consider them as physically distinct. Here, the model construction has somehow forced us to take them seriously. That's one way of saying it, indeed. And you can also show some cancellation type arguments for higher spin correlations. But we should keep in mind that even at t equals 0, we have to sum over the ground state manifold. So this is standard equilibrium statistical physics. And this is true for throughout the spectrum. And once you see this, and some spin liquidity, there's an infinite manifold, you might start thinking about, thermalization and ETH type of things. More precisely, if something like this is true at an ensemble level, just for the ground state manifold, could it possibly be true for some generic initial states, okay, with small energy, small but finite energy density? Could this sum a long time average? Because from this ensemble point of view, we see this liquidity. Could there be some ETH going down to the 0 energy density limit? So this is some question that I'm pursuing with Pranay, actually. So just to give some context, we can do some comparisons. So another model you can think of, which is related to this construction that we wrote down, is this 90-degree compass model. So the way it is constructed is you have chains, Ising chains. And so the Ising chains along this, let's say, x direction is, let's say, the couplings are along x. And the chains in the vertical direction, say, have couplings along z. Okay. So this is the 90-degree compass models. And you will see locally, there are two outgoing x links and two outgoing z links, which was similar even in the previous construction. But for this, it turns out also you have an anti-commuting algebra, but the conserved quantities are, Z2 Ising parities across the full chains, actually. They're not local Z2 conserved charges, but that conservation is across the full chain. And this, because of this non-locality, actually in this model, the degeneracy counting becomes only 2. So once you make it local, the degeneracy counting becomes infinite or extensive. And as is intuitively clear, just depending on the strength of the couplings, if the coupling along the x direction dominates, you have Ising order in the x direction and so on. So this does not forbid Ising ordering. So for liquidity, it's also, from a structural point of view, it's important to have local, conserved quantities, Z2 conserved quantities, and extensively many of them. So another point of comparison would be the Kitaev honeycomb model. So from a model construction point of view, in the Kitaev honeycomb model, we have these XX, YY, and ZZ coupling units. So there are these Ising bonds that have cross-linked in spin space, in orthogonal directions in spin space. So from that point of view, you can consider this model. You take an Ising plaquette along XX direction, and you take another Ising plaquette along ZZ direction, and you cross-link them. Okay. So it's in that spirit, you can compare it to the Kitaev honeycomb model. But as we well know, the local Z2 charges of the honeycomb model all commute, which leads to solvability. And you can do some free fermionization. But in this construction, at least to me, it's not evident if there's a free fermion description or not. And I suspect there is not. And more generally, as far as my knowledge goes, string nets and fractons that were discussed in the last week's conference all have commuting algebras. So perhaps this anti-commuting algebra is a new ingredient. And it helps in this Z2 setup, you can make fairly general statements. Yeah.
I'm not familiar with the Paulis, but is there any reason for putting the anti-commuting like these two?
No, there's no, it's just some personal idiosyncrasy, if you wish. Yeah.
So sorry.
Is there kind of a simplest version of this? Is it the 90-degree compass model, for example, that seems to have the least simplest lattice?
But that is ordered.
But that is ordered.
Yeah.
Okay.
Yeah. So that's
not an example.
Right. So this I would say.
Sorry, I was slightly confused when you ran through those things. So is the square lattice one the simplest one then to think about?
I would say so. Actually, you can make it simpler. So you see, in Kitaev honeycomb model, you're taking Ising bond units and cross-linking them. So this is, at some level, you're directly going to a plaquette unit. But you could take a bond unit. And the smallest thing maybe you could do is take a triangular unit and then start connecting in orthogonal. So this is in X direction and this bond is in Z direction. That is, in my mind, the simplest possible thing, where you have a Z2 conserved quantity here, Z2 here, and the anti-commute. I mean, this is harking to Kitaev's, bond structure. But if you wish, you can think of this as the simplest, the square lattice case as the simplest possible.
Yeah, I mean, how helpful is the analogy to Kitaev here, given that you're not headed for free Majoranas?
Yeah, I mean,
It's admittedly familiar, but
yeah.
but it seems like you're talking about something quite different.
Yes, indeed, I agree. It's just to give a point of comparison. There's no, if you wish, it's a point of contrast, not a point of analogy. Okay. So yeah, so all the familiar cases which are solvable or not generally have commuting algebras, and so I'm trying to make the model, if you wish, stand in relief to those known cases. Okay, so that is the general statement. Once you arrange in some simple model for some anticommuting algebra, quantum spin liquidity is guaranteed, extensive degeneracies and residual entropies are guaranteed. Of course, the more finer details of the spectrum and physics, you need to work harder for that. That you can't make more progress. Yeah. No, it's a valid quantum spin liquid. Yeah. There would be. Right. Yeah. I wouldn't be surprised if there's some intricate entanglement, but I don't know how to sort of say it. No. There are some. So even in Kitaev honeycomb model, you see the bond energies can have power law decaying. So something similar can happen here. Yeah. Yes. Right. Right. Something like that. Yes, indeed. In fact, I will make some statements about this kind of thing as we go along. Yeah, we can say some more, even for a two-spin coupling case. Yeah.
Degeneracy for the spectrum, plaquette correlation will be zero.
No, not necessarily. We'll see some examples. Okay, so this brings. So this part one was I put out a paper last year, middle of last year, and recently we have put out a second paper which focuses on multi-spin variants. But in multi-spin variants, it turns out you can make more progress, somewhat in spirit to the Kitaev toric code. So now consider this model. It's a 4-spin version of the same construction. We again have this same kind of coloring of the plaquettes. And now on this plaquette, I have the product of all the 4 spins. Let's say product of all sigma x's on this one and product of all sigma z's on this one. You can think of it as some corner sharing variant of Kitaev toric code, but sort of more in the spirit, the Hamiltonian is directly composed of the conserved charges, except the conserved charges don't mutually commute, so therefore they are also dynamical, unlike the toric code. And this multi-spin nature will allow for some more progress. So the way to make progress is you kind of do a one-time block decimation. You define an appropriate block variable. And the way to think about it is the Hamiltonian, just cares about these products. Now, from the general algebraic structure, I know that the spin variables, the sigma variables, are not doing anything fancy. They are just zero, just cancellations, and quite featureless from that point of view. So all the, if you wish, the energetics, the many body energetics is hiding in these products, these 4-spin products. So that motivates defining a block spin variable on one set of these plaquettes. And you just define the product, this Z2 parity on that plaquette, as a block spin variable. Okay. So, but the important thing is this is not a equality, but it's in a decimation, meaning this, of course, is consistent with, has 16 states. 4 spins have a dimension of 16 states, but this is a 2-valued variable, and it is just tracking the parities on those plaquettes. Okay, so the spins are doing something, but you are just looking at the Z2 parities, which are contributing to the energies. Okay. So now if you define this, then you can ask, how does the model reduce to in these tau variables? It reduces to something on a square lattice that you can imagine. And this leads to the following. First of all, let's say we chose these orange plaquettes to set up the block decimation. On those plaquettes, those reduce to these red sites. And on those sites, you naturally have just like a transverse field term, because you just the product, correct? And now it remains to work out what is the consequence of the other set of plaquettes. And it's not too hard to see that because the coupling is in the orthogonal direction in the spin space, it just flips the parity of the neighboring plaquette. Okay, whatever, say this parity was +1, whenever sigma z acts on it, the +1 will become -1, the product of the 4 spins. Okay, but it will simultaneously happen for all these 4 plaquettes due to the action of this one. So therefore, you get a 4 tau coupling, right? And you get that 4 tau coupling, you can convince yourself in the orthogonal direction in this tau variable. Yeah. So this, some of you might recognize, is in the conference it was referred to as the plaquette Ising model, which I was not familiar with, but this was studied by Zhu and Moore in 2004. And in some, I found, and so I started looking up what is the plaquette Ising model. There's some website called Error Correction Zhu website. It was written Zhu Moore code. So this is actually a known model. So the energetics of the model is of this 4-spin variant is captured by at an effective level by the Zhu Moore model.
What is the mu bar?
So say this was x, then this is z. Or if this is z, this is an x. Yeah, yeah. So orthogonal directions in spin space. And it's important.
Mu to be something for a particular model.
Yeah, so that's a choice. You choose to block decimate one set of, just like in Kardanov's block scaling or something. But importantly, I got confused for a little while in the beginning that this is distinct and the Wegener Z2 Ising gauge theory. However, this will make reappearance later on. Okay, so it turns out Zhu and Moore had worked out what is the physics of this effective model. And in terms of the plaquette parities, which is controlling the energetics, the system exhibits subsystem symmetries. So you can define products of tau mu's, appropriately along columns and rows, and they all commute individually, individual rows and columns. And so these are subsystem symmetries. It turns out these subsystem symmetries can be unbroken when one of the couplings dominate, and they can break when the other coupling dominates. Where the 4 tau coupling dominates, these symmetries can break. And the ordering was written down, how to think about this ordering. It's an unconventional form of bond order. So you can look up the details in that paper, or I can tell you after the talk. Basically, in short, you take some Wilson loop. The Wilson loop, composed of, I think, the orthogonal tau mu's, tau variables, is the expectation value of that in the ground state is 1 if the 4 tau coupling was all there was, and 0 in the paramagnetic state. Okay, that's the bottom line. And it turns out that plaquette Ising model or Zhu Moore model has a self-duality when the 2 couplings are equal, but this is kind of self-evident in these original sigma models because it is just a simple geometric relation between the 2 sets of plaquettes. So, and this duality was also seen actually by Nusinov and Fradkin by some other kind of mapping to the 90-degree compass model, but that's an aside. But this kind of sort of somewhat unusual dualities becoming self-evident in some expanded Hilbert space actually might be an alternate general way of thinking about known dualities.
So the model is critical.
Yes. They wrote down what is the expected criticality, but I'm not too familiar with that, I have to say. But let me not say anything. Now, there's an interesting thing. Of course, in these effective tau variables, it has the subsystem symmetries, Zhu Moore physics. But the interesting thing, kind of analogous to Kitaev toric code, in the sigma variables, actually there's a hint of topological order somehow. So you can define these non-local quantities, just product of sigma x's and sigma z's. And you can show that these non-local string operators actually satisfy the same algebra that the corresponding operators in the Kitaev toric code satisfy. The details are different, but the algebra is exactly the same. Okay. So therefore, it implies an additional fourfold topological degeneracy on top of what we have been discussing, this local anti-commuting algebra dictated extensive degeneracies. However, there's a caveat, and the caveat is the following. This additional fourfold degeneracy is not quite topologically protected for this particular 4-spin variant, because it turns out in this 4-spin variant, there are additional 2-spin conserved quantities that I did not point out. And your string operators, it turns out you can decompose into these 2-spin quantities. Okay, so whenever you have some non-local conserved quantity, and you're hoping that that will seed some topological degeneracy for you, but if that is decomposable into some local conserved quantities, you don't expect, and you can give an argument why that is not topologically protected. But there is way around it, and you can modify the Hamiltonian in a somewhat fairly natural way for me now. Like on the plaquette, you not only have the product of sigma x's, but you also have product of sigma z's. And once you do this, you kind of lose this additional structure, and this has valid, topological degeneracy. It has all the anti-commuting stuff that we have been seeing till now. And so you can think of that this particular 4-spin model is at the boundary of a valid topologically ordered phase. Okay, it is one of the limits of this more general model.
Sorry, can you explain again?
Which one?
The degeneracy is not the one. And you're saying that this tree can be
Right, local, right. So for example, if I take, so I think this is an x. So this x can be composed of product of sigma x here, product of sigma x here, and so on. So when you rerun that same topological protection argument, you will see that you can generate couplings at essentially second order. You don't have to go to system-wide order. However, there's a different modification which is kind of nice and also natural. So in this construction, we had been focusing from the energetics point of view on these plaquettes. And so, but there are these missing plaquettes actually, which also host some conserved quantities. There's a lot of structure in these models. So in fact, on these plaquettes, all 3 kinds of 4-spin products are conserved, it turns out. And this particular one is of interest because this also, if you just consider this on the missing plaquettes, they are also mutually conserved. So the way to think about this is this last case is essentially like the star charges of the Kitaev toric code. Okay, so this modification, you take the original 4-spin anti-commuting model and you add these 4-spin products on the missing plaquettes. That actually voids the 2-spin conserved quantities. Importantly, the 2-spin conserved quantities that I talked about in the previous slide, just at a structural level, is voided. You don't have that many more. So therefore, this is a valid topologically ordered state. And the 4-spin model you can think of as another boundary of this kind of a topologically ordered state. Okay. And this is actually a local Z2 gauge symmetry. So there is also a local gauge structure hiding in these 4-spin models. Okay. So this, just like star charges are gauge generators, this is the exact same star term of the Kitaev toric code. It's just that the plaquette terms have this anti-commuting structure in these models. Okay, so now we can actually legitimately compare it to the Z2 Ising gauge theory. And just like the argument in standard Z2 Ising gauge theory, you can generate that 4-spin conserved quantity via a perturbative calculation in the.
If you're writing down this in terms of this integrated plaquettes,
right.
Variables, how does this term?
Which one? This one?
Yeah.
In terms of these plaquettes?
Right. So you have a model that we have J's and J's.
Right. Right.
And then if we write down this in terms of this bucket variable.
In terms of the block spin variables. it's decoupled from that sector physics. It's a different sector actually. So that sector is its own sector. The Jumur is in. So I'll make a comment on that very soon. So you can consider this as a variant of the standard Z2 Ising gauge theory. In the standard Z2 Ising gauge theory, you have a transverse field term on each side, and you have plaquette terms along the same spin space direction. Here we just have made them anti-commuting. Okay, that's one way of seeing it. And therefore, the electric charge sector of the Z2 Ising gauge theory is exactly the same, actually. But the magnetic or flux sector is now not clear. It's not the same. It's actually this anti-commuting quantum spin liquid. Okay, so that's the answer to your question. Of course, now you can naturally ask what are the mutual statistics, just like we do in Kitaev toric code. And this is not clear because what is not clear in my head, of course, I can see this this mapping to the Jumur model and so on, but how to sort of think about the quasi-particles in this anti-commuting spin liquids in terms of the underlying spin variables is, at least in my head, it's not fully clear. And so therefore, I don't know how to answer this question of what is the mutual statistics of the quasi-particles in both sectors, which we can, anionic statistics of Kitaev toric code is a very famous result. And this one also has no two spin conserved quantity, so it has also a robust topological order. And one interesting sort of puzzle solving question is, because of these conserved quantities, which commutes with everything else, on the missing plaquettes, the product of sigma y's, you can actually try to set up a loop superposition picture, which we do in standard string nets or Kitaev toric code in the sigma y basis. But it's of course not going to be a uniform loop superposition, which is at some level the simplicity and elegance of the standard string net formalism. But maybe there is some identifiable structure. I don't know. Okay, so that more or less is what I wanted to talk about. There's some concluding comments, but maybe I can pause for. Are there any questions? Yeah.
Even in this JY term,
Mm-hmm.
your anti-commuting plaquette term, local plaquette term, they are still commuting with Hamilton.
Mm-hmm. Mm-hmm.
And,
No, because there's a transverse field now, right? Yeah. So the way to think about it is in the limit when this is small, you still inherit that physics. So that degeneracy is maybe not exact anymore, but that exact degeneracy is now the small band in the many-body Hilbert space. And so there's so if you are at an energy scale, temperature scale higher than that mixing set by JY, right, or something. Yeah.
So you claim there's robust topological order.
Right.
Can you say a few words about the elements in the model and the gradient?
Indeed, that is what I'm asking here. So I can say it's robust. Yeah, it is robust in the sense of algebra. I can tell that this sigma y sector does have electric charges, well-defined quasi-particles, if at least in the multi-spin variant, which will have some dynamics in this situation. But it's just not clear what is the nature of the quasi-particles in this quote-unquote magnetic sector. So therefore, just working out, and I don't see a way of how to set up that, nice thought experiment of exchanging the electric and magnetic charges. So maybe there's a way, but I don't know. So yeah, the final few comments. The structure is actually, because it's corner sharing, it's quite flexible, and you can also generalize it to non-bipartite lattices. It turns out the pyrochlore, you play the same game, and essentially it's a three-dimensional version of all the physics that we saw in the square lattice case. But the Kagome is interestingly enough different. I won't get into the details, but it turns out that the three-spin variant, which is the natural multi-spin variant on the Kagome lattice, lacks subsystem symmetry in the plaquette parities. And more interestingly for me, because the two-spin variants on the square lattices and pyrochlore, you can't say much. You do something and then you're stuck. You just say that it has extensive degeneracy, some spin liquidity. You can't say much. But the two-spin variant on the Kagome actually is comprehensible on the block decimation due to the simple reason that even the, just an Ising plaquette on a triangle. So I have a triangle and just a small Ising triangular plaquette. The local energies are just two values. So therefore, exactly the same kind of things you can do. And it turns out you find a transverse field Ising model type of physics in the plaquette energies for the Kagome lattice. And therefore, you can say some statements about 3 sublattice quantum phase transitions for antiferromagnetic couplings. Blah, blah.
Entropy play a role because earlier you had tau was 2 values, but each of them correspond to 8 possibilities.
Right.
Here one corresponds to 2 possibilities, other corresponds to 6 possibilities.
No, I think it's 4 and 4.
Yeah, it's
for antiferro. Oh, yeah. So with that, I can conclude. I hope you felt that this thing was rather natural in some Z2 setups. It is not quite clear to me how to generalize this anti-commuting algebra to other continuous groups. I had a nice chat with Professor Zhu, and he could construct at least an infinite dimensional version, but with spin models. I don't know. I don't think it's quite natural. There's some additional perspectives. If you recast all of this in the Kitaev representation, from error correction perspectives, these are not stabilizer codes, but rather there are 2 trivial stabilizer codes which have been made, non-commuting. And so therefore, can there be any use for quantum information processing? I have some thoughts there in the paper. And other open questions related, as I mentioned during the talk, to thermalization and so on. And one other very interesting thing for me would be if one can come up with some exactly solvable versions of this in the sense of spectrum. And with that, I acknowledge my collaborator, this is Harsh. And maybe these quotes, as someone asked, was a little frivolous, but okay, I think I'm allowed to do things in my own paper. But I leave it to you to judge whether it's, at least I hope I convince you that it's at least not this. So the details are in these 2 preprints, and I thank my funders, Government of India and IIT Bombay, and also Okinawa, OIST, and also Dresden APKs, which supported a sabbatical stay. So thank you all for your attention.
So obviously, exactly soluble would be great, but what about numerics? Is there? Can you do something a bit more blue collar to explore one of these things and get a sense of what the spin
that
physics
should be
is
done.
like?
That should be done. That's on my to-do.
Has it been done, or that's what you're doing with Pranay? Or?
That's one of the things we are doing with Pranay. Yeah.
Is there anything that you can say about that? What you have done, or what you are doing, or what you expect?
Well, we are in the preliminary stages. So the first thing that we were verifying is just the degeneracy counts, and they seem to be working, even though they seem, secure. The next thing that we are now going to look into is standard things like level statistics, or even, just doing some long time averages, or just directly verifying, the ETH statement that some local observables doesn't have any dependence on which state you take the matrix element of. So those are the kinds of things we are looking into, but there's nothing concrete as of now, because we are using exact diagonalization at the moment. Yeah. Yeah. Yes, and then you don't get to a big system size. So it's not clear to us right now if we can, if it will be enough to say something strong, but we'll find out. Yeah. I'm not sure. Yeah.
It would be nice to know things like those.
Right. Yeah, modulo this topological business. So my expertise is more in quantum Monte Carlo, and that's where when you have these multi-spin couplings, the updates become a little tricky. So it's not evident if it can be studied. Let's say if I'm interested in the just plaquette energy correlators, just how to update the ensemble, etc. It's not quite clear, but maybe some MPS techniques, as you're suggesting, may be possible for, yeah.
About like the free fermion thing,
Mhm.
I don't know, like there are these like papers that like Fermion and Shannon about like drawing like frustration graphs. And,
Right,
like,
right.
checking with the graphs. If the
Right.
model is Fermion or not.
Right. No, this one is not. Yeah. Yeah.
Okay, so you check it. Okay.
Yeah. In fact, the first part, which I didn't mention the reference, those, orange line, green, those fall in that category.
I see. Okay.
Those are free fermion, because as I said, it was Jordan-Wigner solvable. This, as far as I mean, there are some comments on the paper if you're interested, why something like that might not be true in this one. So we just recast these models in the Kitaev representation, and you see that any kind of fermionic thing might not just be, yeah, but it's an intuitive statement.
So any further questions? Okay, if not, let's thank Sumiran again.
Thank you very much for coming.
The last minute post I did, I made an enormous typographical error in the type.
Maybe on purpose.
It was fine. Well, you have to appear in conflict. And I gave it that way. They like your results.